Cool. We are back, and this time we're gonna be doing some um, biconditional. Um, you could call it biconditional rules of inference or biconditional um, rules of equivalence and stuff like that. Uh, now, the thing is, a biconditional, say something like alpha um, double implies beta, or alpha if and only if beta. This is sort of like a symmetric operator in the sense that this is we've gone over how this is gonna be um, equivalent to saying beta double implies alpha, right? Um, and yeah, so this property is also called commutativity, right? So because of this, there are certain things that you can do. Oh yeah, also remember that this also means alpha implies beta and beta implies alpha. So given all of this stuff that we know about the biconditional itself, there are certain things that we can sort of um, add to our repertoire of rules of inference or rules of equivalence. And that is gonna be something like, for example, we have the traditional modus ponens, right? We have, um, so for example, we have alpha implies beta, and then you have alpha, and then you have therefore beta, right? But we know that alpha double implies beta, or alpha if and only if beta is a conjunction of alpha implies beta and beta implies alpha. So let me show you what we can get from that. So we know that sorry, one sec. Yeah, we know that alpha double implies beta, or if and only if beta, whichever you wanna call, refer to it as. So that's alpha implies beta and beta implies alpha.
That's the material equivalence, right?
That's the material equivalence. One of them anyway. So since this is a conjunction, there is a rule that I can apply and get alpha implies beta from it.
You can just do simplification, right?
Do simplification, exactly. And if I know this is true, if I know alpha is true, then I can get beta is true. And that's just gonna be a modus ponens. So I started from here and here, and I reached here, right? Which means I can simply skip this step and get to this directly. And that is gonna be like just a modus ponens, but with a biconditional instead of a conditional. So when we're talking about biconditional modus ponens, we can just call it, just biconditional modus ponens. And then the rule of inference basically will be like this. So it's an argument form, so it has to have the form of an argument. So that's P1, that's P2, and that's the conclusion. So if you look at this basically looks like a modus ponens, except that there is a biconditional instead of a conditional. So that's why we kind of call it a biconditional modus ponens. Okay. So, that's the first rule of inference. So, if you can do this, if you can do the modus ponens, there's nothing stopping you from doing a modus tollens. So, by extension, you can simply get a biconditional modus tollens, and that will just be 1 to C conclusion, and then you have alpha if and only if beta, and then you have not beta, and then as the conclusion you have therefore not alpha. So that's just going to be another rule of inference, biconditional rule of inference. Then the other would be just a hypothetical syllogism. And it's basically the same principle. So it's going to be like a biconditional hypothetical syllogism. So what you can do is you have 1, 2, and C. The first premise will just be alpha if and only if beta, beta if and only if gamma, and then you have alpha if and only if gamma. And the idea is basically the same. If you have this, you can derive alpha implies beta from that. If you have this, you can derive beta implies gamma from that, and we can just straightforwardly apply the regular the regular hypothetical syllogism to this, and we can basically get the hypothetical syllogism, which is gonna be alpha implies gamma, and you can do it in the other direction. You can get beta implies alpha, you can also get gamma implies beta, then you can get gamma implies alpha, and the conjunction of alpha implies gamma and gamma implies alpha is the same as alpha if and only if gamma, or gamma if and only if alpha. Are you following that?
Yeah, so that when you go the other way, you start with premise 2, and then you make a gamma implies beta, and then you make with premise 1 beta implies alpha, right? And then so you do it another way, and then you do a
Yeah, you
conjunction
can.
with the first hypothetical syllogism that you did going forwards.
Yes. So you can basically get enough information from these two premises to perform two regular hypothetical syllogisms, and then you can just conjoin both the both the conclusions of the two hypothetical syllogisms to get um, the material equivalence of this, and from there you can work your way back to this.
Yeah, I'm following that.
Okay. So yeah, those are basically like three rules of equivalence that we have over here. So we have the biconditional modus ponens, you have the biconditional modus tollens, and you have the biconditional hypothetical syllogism. Very straightforward, right? And so that's three more rules of equivalence that you have. Rules of inference that you have apart from the previous 12 or whatever we have learned before. I don't remember, whatever that is. Yeah, I think it was 12 rules of inference, right? And then we did some tricks last time. So we add those two. So we got 18. So we have 12 rules. I think 12 rules of inference. Was it 12? One sec. Let me just.
Oh, wait, so we had modus ponens, modus tollens, disjunctional syllogism, hypothetical syllogism, conjunction, addition, simplification, constructive dilemma.
Oh yeah, eight rules of inference, right? So eight rules of inference and 10 rules of equivalence. And on top of those, we added a few tricks last time, right?
Yeah, so making conditionals, switching
Yeah.
antecedents of a nested conditional, negated conditionals, simplifying antecedents and consequences, and combining conditionals. So in terms of like tricks, we had about 5.
Right. 6 tricks.
Making conditional, switching antecedents of a nested conditional, negated conditional, simplifying antecedents and consequences, combining conditionals. Oh yeah, and then also
Tautology.
the 6th one was when we have like it leading to the negated. I can't remember the name of the trick, but
Yeah, I don't think it had like a. Yeah, I don't remember it having a name per se. Um,
oh
but
yeah, you
yeah,
got it there on the
whatever
screen.
that is,
Yeah.
you know, whatever
Yes.
that is.
Yeah.
Yeah,
I see it. You got it there. I was looking at my sheets.
yeah, yeah,
But yeah, it's like when you just have the variable implying its negation, it just is equivalent to its negation.
yeah. Right. Yeah. So that's like okay. So we have 8 plus 10, that's 18, plus 6, that's 24, plus 3, that'll be 27, and then we are going to do some rules of equivalence right now. So yeah, we have a lot of rules to play with.
Some of the derivations have been very long.
Yeah, they've yeah. Yeah.
Yeah, like the derivations to do it on stream, it's not very interesting.
Yeah, I know. Yeah, okay. So let's go to the rules of equivalence. So the first one that we can talk about is the biconditional De Morgan's law.
Yeah. So the last 3 which we did, it was rules of inference.
Inference, rules of inference. So I'll just mention that here. Rules of inference. And then we have rules of equivalence. I'm writing in short because it's a pain to write with some mouse. But yeah, anyway.
Because your pen's not working, right?
Yeah, I gotta figure that. Anyway. Yeah. Okay, so we have the first one, which is just gonna be the biconditional itself and its negation, basically. So when we say that alpha if and only if beta is false, what we essentially mean is that it is one of those cases where in the truth table either one of them is true and one of them is true and the other is false. That's what we mean when we say that like a biconditional is false, because a biconditional is true when both the atomic propositions have the same truth value, and it's false. So yeah, did I say true? Yeah, the biconditional is true when both of them have the same truth value, and it is false when they have this different truth values. Now, for a biconditional to be false, there are 2 ways, right? The first atomic proposition could be true and this could be false, sorry, the first one can be false and the second one can be true, or the first one can be true and the second one can be false, right?
Yeah.
Yeah. So you can just express this a bit differently. What you can basically do is you can just replace this with alpha double implies beta, but the alpha is false. So that's one way of doing it. And I can sort of show you why, because okay, so let's sort of prove it for once, and then you can make sense of the others. So let's say I have negation of alpha double implies beta. So this means that it is a negation of alpha implies beta, and beta implies alpha. So from here you can apply the regular De Morgan's law. So what you can do is, so what's the regular De Morgan's law over here?
You put the negation inside and you flip the sign.
Right. So you get alpha implies beta, or beta implies alpha. And if I just expand this, what will I get?
What do you mean by expand?
So when is a conditional false?
The conditional is false when the antecedent is true and the consequent is false.
The consequent is false. Okay. So the antecedent is true and the consequent is false.
So this is when it's like, yeah, when it's
The same thing over here, right?
okay. It's just to get the truth condition, right?
Yeah, just got the truth conditions. And now,
And then what's happened to the negating well outside the brackets, the negation sign.
which one?
So the on 3
Uh-huh.
premised. So you've got the negation there on the left outside the bracket.
Yeah.
So what have you done with that sign there to get from?
Oh, okay. So what I've just taken I've skipped a step over here. But ideally what you're supposed to be doing is not alpha or beta. That's the truth condition. And you're supposed to do beta, sorry, not beta or alpha. One sec. And then you can do another De Morgan's law.
Okay.
So you have alpha and not beta, or beta and not alpha. Okay. Now, remember constructing conditionals.
I'm getting material implication,
Right.
using the material implication.
Yeah.
So then it's it depends what we want to take as the antecedent, but if we, for example, we want to take the negated beta as the antecedent, then it'll just be beta implies alpha.
Well, notice these. It's a conjunction, right? Which
It's a
means,
conjunction. Yeah.
yeah, which means which means both of them have the same truth value. Alpha has the same truth value, and not beta has the same truth value.
Yeah, material implication we do when it's a disjunction. Yeah, so yeah, just forget what I just said.
Yeah, you can also do it with, you can also form a material. So what you can do is, this is perfectly fine from
Um,
here to here.
uh, how how did you do that?
Yeah.
Because
So it's a conjunction, right? Which means both of them are true.
yeah,
And what's the truth table according to, what's the truth table say of the material implication when both of them are true?
the truth table for the material
For the
implication
material conditional, yes.
for material conditional or material.
Yeah.
So material conditional when uh
Material
so if
conditional,
we
material implication, both are the same basically. But yeah.
so if we're looking at 6, then it's true when for every condition as long as like alpha is not true and not beta is false. If you've got both of that, then not alpha implies not beta is
Right, but what
false.
I want to ask is, when alpha is true and when not beta is true, um, what is like what will be the truth value of this?
True value of this when alpha is
True and not beta
true,
is true.
it'll be true.
It'll be true, right? So from this you can just get this directly. Did we do that last time?
I can't remember.
Um,
We did a lesson where
oh look, yeah, we did it here. Check this out. This part.
what were you doing here? Just to refresh my memory.
Yeah.
Like
So
what lesson was this?
this was making this is under making conditionals.
Okay, yeah. In the that this was like last lesson, right?
Yeah.
Yeah, making conditionals.
Yeah.
So yeah, what did we do?
So if we have a if a conjunction is true, the implication is automatically true. If we have a conjunction of alpha and beta, that is true,
Yeah.
then the implication is just automatically true.
Okay. Because yeah, I for the not for yeah when we had the negated p, we did some sort of proof, but yeah, I kind
Yeah.
of remember how exactly we just derived that equivalence. But it's just basically what you're saying. It's because when both of them are
Yeah,
true,
both
then
have the
the
same truth value, right? And if both have the same truth value, um, on a table of material conditional, when both are true, then the conditional is true.
and they'll also if they're both false, then the conditional will also be
Will
true, right?
also be true, exactly. So here we
Okay.
have a conjunction, which means both are true. A conjunction is only true when both are true.
Yeah.
So so from there you can get alpha implies beta, and you can also get beta implies alpha. And from these
Yeah.
two,
Going.
you can get alpha if and only if beta.
By doing a conjunction of them.
Exactly, yeah. So, coming back here, we can just directly do alpha double implies, or if and only if, not beta. Okay? Or beta if and only if not alpha, right?
Yeah, because you just assume that, yeah, we've got the two conditionals, and then we just do a conjunction for
Exactly.
both of those two brackets.
Yeah. So when I say um, it's false that um, alpha if and only if beta, it can mean one of two things. It can mean this or it can mean this. And um, that's just just the rule of biconditional De Morgan's law.
Oh, you said it can mean this and this. What were the two things that you said?
Alpha if and only if not beta, beta if and only if not alpha. Now you can obviously do another step where you can just simply um, do a commutation on both sides, and you can get this
Okay,
form.
yeah.
But yeah, so I'll just move this out of the way. So yeah, so this is one thing that you can get, and you can also get this. Or you can write it like this, not uh, alpha if and only if not beta.
And you can just represent it however you want with the commutativity. You can.
Exactly. Yeah, you can represent it however you want with commutativity.
So yeah, there's like four options.
Yes. So that's the De Morgan's law. And as just we discussed commutativity, the other rule obviously is just biconditional commutativity. Um, so if you have alpha if and only if beta, um, you can derive um, beta if and only if alpha from there. Um, so that's just what commutativity is, right? Similarly,
So that one we would prove just using truth tables, or like
yeah,
what would
you
be.
can you can either do it by truth table, or you can what you can do is just do a material uh, equivalence rule. So you get alpha implies beta and beta implies alpha. Do a commutation of the conjunction, right? So
Mhm.
the regular conjunction. Yeah. So
Yeah,
then you get beta implies alpha and alpha implies beta, and then from there you
yeah,
do another material equivalence, and then you get this.
yeah. Got you.
Yeah. So if you want to do a natural, like a syntactic natural deduction proof, that's the way you would do it. You can also do a semantic proof like a truth table. You can also do a semantic proof like a truth tree, which we will talk about. I'm not sure if we will be able to cover it today, but yeah, I think we should restrict this session for biconditionals, and then do a fresh session for truth trees.
Sounds good.
Yeah. Um, yeah. So you can get this. This is just this just is the commutation. The other thing you can do is a biconditional inversion. You remember inversion?
Not really.
Do you
Yeah.
remember
Uh,
contrapositives?
Contrapositives, yeah.
Okay. So what will be the contrapositive of alpha implies beta?
It would just be not beta implies not alpha.
Correct. So inversion is just contrapositive and commutation.
Okay.
So you know this is the contrapositive, right? Now if I do a commutation, I'll get not alpha. Uh, Wait, I can't do that over here, but I
Yeah.
can do it over here. So the contrapositive of this will be
Oh no, yeah, we did actually. Yeah, we talked about the four types of conditional: the converse, inverse, contrapositive, and normal
right,
conditional.
right, yeah. So yeah, but what I was saying is you can't derive not so if I have this
Yeah, you can't do commutation on a
on a
conditional.
conditional exactly, but you can do commutation on this guy. So I can just do a contrapositive, and then I can do um, not alpha, not beta. And an easier way to think about it is that think of it like alpha and beta both are true, so the conditional is true. Alpha and beta both are false, so the conditional is true. So this conditional, this biconditional is equivalent to this biconditional, because even here both the propositions have the same truth value. Right?
Uh, could you sort of repeat that
Yeah,
again?
yeah,
So
sure, sure. So
we've got the first premise, the conditional alpha implies, well, yeah,
it's
just
a
alpha implies
biconditional.
beta.
Yeah,
Yeah, yeah, by conditional.
yeah.
So I'm not sure how you went from
So
first
I just
premise to
did
the second.
commutation here.
Oh, but how did you get the second premise?
Oh, I did a contrapositive.
So you just contrapositive using the
Yeah. So
so you
yeah,
expanding out the
yeah. So I took a
biconditional.
shortcut, but you can do this, right? Beta implies alpha, right? So this the contrapositive of this will be, and the contrapositive of this will be, right? And then I just did a material implication. Sorry, a material equivalence.
Yeah, so
So I got this.
yeah, I see that, and then after that, to get from two to the conclusion, well, we can also do like a proof. Although, yeah, we probably don't need to do it, but similar to how we would do it for the commutativity, we would like
Yeah,
just yeah
yeah,
expand it out and then do a commutativity, and then do another material equivalence and
exactly.
come back. Yeah,
Yes.
to
So
get
that
the
we
not
can do
alpha.
that. But so what I wanted to show you is that you don't even have to think about it in terms of a proof. You can simply think about it in terms of a proof, in the sense that you don't have to think about it in a natural deduction kind of way. It's just simpler to think about it in terms of like a truth table. So if you have PQ, P double implies Q. Um,
ETFF, right?
yeah, T F F T F F, and then you have T F F T, right? Now similarly, if I just do the negations, it's just going to be ff, right? These are going to be ff, and ff is true.
Yeah.
This is going to be whatever, ft instead of tf, and that's going to be false. You can also do a sorry, this is going to be a tf, that's also going to be false, and this is going to be tt, which is going to be true. So if you look at this, these are logically equivalent because the truth table is the same.
Yeah, I got it.
Yeah. And an even simpler way of thinking about it is that alpha implies alpha if and only if beta just means that both of them are true, but it's also true when both of them are false. So this and this are equivalent because this is true, this is just a case where both of them are true, and this is just the case where both of them are false.
Mm.
So that's another way of sort of looking at it in terms of the truth values. But yeah, so that's just the biconditional inversion rule. Another thing that you can do is association. You remember association?
Yeah.
Biconditional association. So what will that be in terms of non biconditional operators?
In terms of non-biconditional operator, there's alpha or and then you open a bracket, beta or gamma.
Okay. Sorry. And that's equivalent to
It's equivalent to open bracket,
okay.
alpha or beta, close bracket, or gamma.
Yeah, exactly. So notice that this is a symmetrical operator, right? And even this is a symmetrical operator. So you could just do the same thing with this. So I can just
What do you mean by symmetrical operator? Let's see.
I just mean sorry, thanks. I just mean you can perform a commutation.
So, in we can form a
So any
that
operator where you can perform a commutation is symmetric.
so anything with a conjunction or disjunction.
Or biconditional.
Okay.
So those three are symmetric. So biconditional, conjunction, and disjunction, these three are symmetric. The material implication is asymmetric because you cannot perform a commutation. And the negation is a unary operator, so there is no scope of, it's beyond the scope of commutation. So here you can simply put a biconditional and that will be valid. So this is biconditional association. Now I forgot to mention that you can also, I mean we did it over here, but you can also perform a contrapositive, right? But I didn't mention it because I used it as like I used it in a proof over here. But yes, another rule of equivalence is a biconditional contrapositive. The same thing will be a true for like a biconditional converse. So what's the converse in non-biconditional operators?
It's Q implies P.
Q implies P, right? Which is sort of a commutation, right? So we have already discussed that over here. So this you can think of it as a converse. Um, you can take the inverse and you can also do a contrapositive. And this all becomes possible because the biconditional is a symmetric operator.
So the contrapositive is just the premise number 2, right?
Yes, this is the contrapositive. So like one of the differences between like a material implication or a material conditional and a material biconditional is that it's not symmetric, and because it's not symmetric, um, the 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 regular conditional and the contrapositive of the conditional are logically equivalent, but the regular conditional and the converse is not logically equivalent. The regular conditional and the inverse is not logically equivalent, but the converse and the inverse are both logically equivalent. But
Yeah,
here all
we
four
briefly
forms
touched
are
on this.
yeah.
Here, could you repeat that? Sorry.
Yeah, here all four forms are logically equivalent.
So, when you say all 4 forms, you mean
Yeah.
the
So
what are you referring to by all
so
four
for
forms?
example, alpha if and only if beta, that's one form. Beta if
Yeah.
and only if alpha, that's one form. Not alpha if and only if not beta, that's the third form. And not beta if and only if not alpha, that's the fourth form. So this one, this form, this form, this form, and this form, they're all logically equivalent. But
Okay,
that's
so all 4
not
types
true.
of conditional. Yeah.
Exactly. But that's not true of conditionals, because conditional in the conditionals, two of them are logically equivalent to each other, but the other they are not logically equivalent to the other two.
Mm.
So yeah, that's something worth noting. So yeah, I think that should be good. So we are done with. Hopefully, we are done with all the rules of inference with respect to biconditionals. It's pretty straightforward. There was nothing very complicated over here. So we did the biconditional modus ponens, we did the biconditional modus tollens, the biconditional hypothetical syllogism. Um, we also did the biconditional. So we did rules of equivalence, where we did biconditional De Morgan's law, biconditional commutativity,
Sensitivity. Yeah.
the inverse, and then we did the association.
And
So
also there's a contrapositive.
they also did the contrapositive, exactly. So yeah,
And the association, we didn't really show the proof, but it could be also possible to do a very long proof where you
yeah,
expand it all out and just go back to
yeah. You
like
can expand all of this and rearrange it using just regular, um,
commutativity.
yeah,
Yeah.
commutativity, association, and stuff like that. Uh, but yeah, like, if you want a shorter proof, you can just do a truth table. Um, if you want a natural deduction proof, but you want it like relatively shorter, what you can do is you can just do an indirect proof. I'm not sure if we have gone in. I don't think we have gone into like details of how to do like an indirect proof, right? I think that's coming.
Well, in direct proof, that was by reductio.
Reductio, yes, reductio ad absurdum.
Yeah, we briefly. Well, yeah, we did a bit on that, and
Yeah,
then also conditional proof we touched upon.
yeah. So yeah, we
Uh,
got like we did the proof by contradiction, reductive ad absurdum thing. So that you can use over here. So there's no shortage of proof strategies. We have a lot of proof strategies. um,
yeah, so yeah, we've got just using rules of inference, so just a proof, right? And then
yeah,
so just by
like
starting
a
with the premises and using rules of inference or rules of
yeah,
equivalence, and then that's what's the name of that proof again?
natural deduction.
Natural deduction, and then we've got indirect proof, and then when we have a conditional, we can do a conditional proof,
Yeah,
and then next time we'll see proof trees.
truth trees. Yeah, which are like really interesting to me personally, because you can basically do any proof with it. Any proof in propositional logic, you can do it with truth trees. Any proof in first order logic, you can do it with truth trees. But for that, we'll have to first tackle first order logic, which is another giant on its own. But once we understand first order logic, doing tree proofs with first order logic is really straightforward, because you only need to remember a couple more rules of inference when you're applying it, um, and you can just straightforwardly get it. So it's no big deal. But next time is going to be like a comprehensive session on how to do truth trees with prop logic. So that will be like
Cool.
really interesting. Yeah.
Cool. And then, yeah, in the meantime, people listening, they can try, I guess,
Yeah.
what's the exercises in the book,
Yep.
3.7a,
Yep.
and then 3.7a is just using, yeah, already formulated
Yeah.
premises and using variables and operators, and then exercise 3.7b is to translate and then derive the conclusions.
Right. So
Cool.
yeah. So
But yeah,
these are like really straightforward stuff that people can practice while they're keeping up with the sessions.
yeah. But yeah, it's a big volume, so
Yeah.
yeah, it can be kind of daunting. It's a lot
Yeah.
of to remember
Yeah.
and keep on maintaining.
Yep. Yeah. Cool. So I guess we'll catch each other in the next session. So I'll just end the
Great.
recording.